Hi, and welcome to question 7 of the 2024 Leaving Cert Ordinary Level Paper 1 in Maths. So question 7 is a fairly long one. Part A here, part A1 says, during an experiment, the number of bacteria in a dish can be modeled by the function P of t is equal to t to the power of 3 minus 6t squared plus 6t, must be a 6, plus 20. Where P of t is the number of bacteria, so it's the number of bacteria in thousands, and t is time, as we'd expect, since the start of the experiment with the time being between 0 and 5. So 0 is less than or equal to t, is less than or equal to 5. T is an element of R, which means it's a real number, so it can be any number. So complete the table below to show the values of P of t for the given values of t. Now it gives us two that are already done out. We can use a calculator here. For example, if we do it by hand, okay, I want to get rid of some of this fluff. I'm going to use the value of 0, okay. So what's P of 0? Well, I put 0 in instead of the t value all the way through. Now what's going to happen is that each one of these terms, that's going to become 0, that's going to become 0, that's going to become 0, and you're going to be left with 20. Now we come along and do the same thing, except this time we replace the t by 1, put it through our calculator, and we'll get an answer of 21. Then for value 2, which you can check, if you put 2 in instead of t, you should get a value of 16. That'll confirm you're right. Keep going with the calculator and work out the last two values. Job is done. So all a model is doing is describing a certain behavior. Okay, this is a third order polynomial, or sometimes it's called a cubic. It will look something like that, and it's describing the growth rate. For whatever reason, the number of bacteria go up initially, then down, and then start going up again. It could be due to food or whatever is in their environment. So that's that, part A, part 1. Now part A, part 2 says, draw the graph of P of t on the axis below for, again, 0 is less than or equal to t, is less than or equal to 5, t is an element of R. So all this is kind of fluff. It's really just saying graph what you found. So whatever you found there, even if it's completely like wrong, if you graph that on part 2, you'll get the marks. Okay, so this is what I found. So the first one there, I put 20. So when x or t is 0, y is 20. Okay, the next one, when t is 1, y, or in this case P of t, is 21. Then 16, then 11, then 12, and then 25. And what I should have done in the notes was, I don't know why I didn't do it, is join this together. What I do know, it's really hard to draw a non-straight line and following that curvature. So again, the bacterial numbers are starting off, going up a little bit, then down, and then back up again. So that's the graph, fairly handy in the scheme of things, especially when whatever you find in part A1, if you graph that, you'll be given full marks. So 7A, part 3 and 4, but we'll go with 3 first, says find P prime T, the derivative of PT, and remember that it gives you, again, it gives you the model. So we'll find P prime T, or the derivative of PT. So we need to differentiate each one of these different terms. So the first one, we're multiplying power by number in front. That's the power rule of differentiation. The number in front there is 1. So power by number in front is 3 times 1. And then step 2 says we take 1 away from the power, 3 take away 1. Now that's going to ultimately give us 3 by 1 is 3t to the power of 2. And that's always how you differentiate something like that. Now the next term, minus 6 times t to the power of 2. So again, multiply power by number in front, and then we take 1 away from the power. Now that's going to give me minus 2 by 6 is minus 12 t to the power of 2 take away 1 is 1. Now my next term can do the same thing, but there is a power of 1. Now let me just clear off some of this. There is a power of 1 on that particular term. So the power rule can apply. So again, it's, and I'm going to run out of space, it's power by number in front, and then take 1 away from the power. But that's going to end up giving me plus 1 by 6 is 6 by t to the power of 0. Okay, now t to the power of 0 is the same thing as 1. So that's going to be 6 by 1. And our last term here, the 20, any number when differentiated always turns into 0, which is going to go away. Now that's going to give you an answer when I clean it up. 3t squared minus 12t plus 6 by 1 is just 6. 0 we don't need to write. And that's my answer. Now it says then find the value of p prime 2. Okay, so remember this is p prime of t, so it's general. We're going to be more specific and put 2 in instead of the t all the way through, assuming I don't make a mistake. Now that's a calculator job, but I can do it by hand. 2 squared is 4, by 3 is 12. Take away 12 by 2 is 24, plus the 6. That's the same thing as 18 take away 24, which is negative 6. Okay, now that might seem wrong, but at t is equal to 2, is the graph going up or down? Well, let's just double check. At point 2, the graph is going down, which would indicate a negative slope. And ultimately, that's what differentiation does. It's a way of finding the slope. Okay. Now, in a linear model, that's not that difficult. But in a nonlinear model, which this is, differentiation gives us a really powerful tool to be able to predict, which is really what science is all about. Now, there's the answer. Now, part 5 says P of 4 is equal to 6. Explain what this means in terms of the number of bacteria. So when T is equal to 4, the number of bacteria, okay, is equal to, like, I think it's 6,000. I said per thousand. Okay. So after 4, no, I'll go look at the answer here. Hours. After 4 hours, the bacteria are reproducing and their population is increasing. This is positive. Okay. So the numbers are going up by 6,000 per hour. That's all. Okay. Now, part 7, part B, part 1 here says the number of bacteria in a different experiment can be modeled by the function k of t is equal to 3,000 times 2.7 to the power of 0.5 by t. Now, this is an exponential function. Okay. So normally when bacteria are growing, they start off slow. So this might be bacteria, maybe time and number. It starts off slow and then starts to get faster and faster and faster. And this is indicative of the doubling nature of most bacteria. So depending on the speed that they grow, that can be pretty rapid. So the initial few hours or days, depending on the species, can be slow. But as they take hold, their numbers can increase dramatically. And that's where your immune system will hopefully kick in. If your immune system is not doing the job, you may need antibiotics. Or, well, there comes a point, if the bacterial numbers become overloaded, you're in serious trouble. So this is our model, okay? That's what we're concerned with. So it says K of t is the number of bacteria and t is the time in hours since the start of the experiment, with a range or domain of 0 is less than or equal to t is less than or equal to 8, and t is the limit of r, which again just means it's a real number, so it can take on any value. It says there are 3,000 at the beginning of the experiment, and then the model starts from there. So use K of t to find the number of bacteria after 1 hour and after 2 hours. So we have two things to do here. 1 hour, okay. So then we're going to use the model. So we're looking for K of 1 is equal to 3,000 multiplied by 2.72 to the power of 0.5 times 1. Now that's going to be the same thing as K of 1 is equal to 3,000 by 2.72 to the power of 0.5 by 1 is 0.5. Now using the same logic, k of 2 is equal to 3000 times 2.72 to the power of 0.5 times 2, which is going to give me an answer of k of 2 is equal to 3000 by 2.72 to the power of 0.5 by 2 is 1. Now in the notes, I'll have that done out. There's the first one. The calculation through the calculator gives me 4,947. And it says to round up to the nearest whole number. So the 7 here is what matters. That's greater than 5. So it rounds up to 4948. Okay, bacteria. After 2 hours, we get similar like calculation. Throw it to the calculator. I got 8160. Okay, so in this particular situation, the bacterial numbers are increasing every hour. Okay, which again, in exponential growth, which is is what we'd expect. So it's fairly straightforward. Now it says after n hours, there are at least 35,000 bacteria, according to K of T, the model we just dealt with, where n is an element of n, which means it's a natural number. So they are all the positive whole numbers. Okay, 1, 2, 3, whatever. By continuing the pattern above or otherwise, find the smallest value of n. Now, there are a few different strategies for this. I'm just going to use the notes because they're already done out. And there's our model. Okay, we were given in question 7, part B, part 1. And I'm just going to use trial and error. So I could just do, it was on 0 and 1, okay, in the previous answers. And I'm just going to do 3, and I got 13,000. After 4 hours, there's 22,000, which is less than 35. After 5 hours, there's 36,000. So that's over 35,000. So our number of hours must be a positive whole number. So either 0, not 0, 1, 2, 3, 4, 5. Okay. It can't be 5 hours because that's over 35,000. So it must be between like 1 and 4. And they're looking for the biggest. Okay. The smallest value of n that satisfies that. And that's the answer, n is equal to 4. So that's it. So trial and error could work there. You could probably solve it using an inequality. That'd be totally legit too. You should get 4 as an answer. But sometimes trial and error is a perfectly rational thing to do, just as long as the answer is easy to find, But usually they'll give an indication if it's not. Now it says after this is part B, part 2. Now in the notes, I started to do that other method and I just never finished it, so I must go back and do that for the notes. So actually, that's the end of question 7. Okay, I thought it was longer. So as always, if you want to copy the notes I'm working off, just send me an email at shanetroy@gmail.com. Like and subscribe to get access to more playlists, and see you on question 8.